Okay, perfect. So Elsa, yeah, thank you again for the introduction. My name is Jensen Woodfelt. I've been looking at this project as part of the Earth Data Analytics program through CU Boulder, and specifically am looking at how we can measure the impact of green infrastructure projects on stormwater capture in urban environments. Ideally, this project started out with wondering, hey, can we take spatial data, satellite imagery from space, and use it to measure and validate the role that green infrastructure projects play in a very dense urban environment. And particularly in this case, green infrastructure projects include geoengineered features like stormwater spreading grounds, bioswales, water retention ponds. And the goal was that we could look at using a very high resolution spatial data set like Sentinel-2 HLS, which we'll talk about in a second, to validate that remote sensing role there and validate the role that they play within an urban environment. So particularly, I was looking at several stormwater spreading grounds in the Los Angeles area and primarily ended up focusing on the Eaton stormwater spreading grounds, which is located just outside of Pasadena. And for a little bit of background on why this might matter, I'm particularly interested in this. I work in the kind of built environment space, particularly looking at kind of sustainability consulting for building portfolios. And a lot of times these green infrastructure projects are really something that are kind of either discounted or not quite understood as part of the value that they bring in the overall built environment, but they play a really critical role in helping to redirect and recapture stormwater, particularly in these dense urban areas, which has the benefit of recharging local groundwater resources, but also helping to flatten the peaks in stormwater flow there. And while this is a big issue right now, it's likely going to be an even bigger issue here over the next century, as cities in particular are looking for ways to combat the effects of climate change here and changing precipitation and climate norms. So starting out here, there's three primary data sources that I was working with through this analysis. The first was the Sentinel-2A HLS data. Primarily, I was actually looking at the Landsat harmonized version, which is the L30. It has this 30-meter spatial resolution, and particularly, I was looking at about a 5-year span of data there. I had used that the raw TIFF files there from Sentinel-2A and cropped those using open data from LA GeoHub and LA Open Data Hub there for particular locations of stormwater spreading grounds and city shapefiles. And then lastly, had used the iMerge GES precipitation data for daily max precipitation values. They were subsetted there to the LA region there, and for the date time that I was looking for, which back to a point that Jackie made earlier, definitely helped to lessen the amount of raw data that I needed to take down from the NASA Earth Data Search site there, which was thankfully very, was worthwhile for my computer's computing resources. So this analysis really focused primarily on using the normalized difference moisture index, or NDMI, in order to measure that impact of the stormwater spreading grounds, particularly as it relates to the moisture index of that area. And it's important to note here that NDMI, in this case, it measures the difference between the near infrared and shortwave infrared bands there. And it actually is focused more so on looking at moisture as a relation to vegetation content rather than particularly soil moisture. And that was one of the big challenges in this analysis, in this project, where I needed the high resolution availability of the Landsat and Sentinel-2 HLS data versus something that has a much lower spatial resolution like SMAP. And in that case, NDMI was the kind of best resource, at least, to see about analyzing those water flows and water values there as a result of the water capture from those stormwater spreading grounds. And one thing Avra and Kristen just mentioned there as well. So validating the Sentinel-2 data, and particularly the cloud masking aspect, was a challenge in this as well. I do blame maybe a little bit of the coastal aerosols and maybe the LA smog on this a little bit, but there certainly were a number of different challenges in through the cloud mask, either masking too much of these site areas and project areas, or letting kind of bad data pixels slip through in these cases. But thankfully, through a couple of different filtering functions there, was able to process the data in a way where we could keep just the meaningful data resources here. And just to move ahead here, I wanted to show an example of how that NDMI was calculated for these different project and site areas. So I specifically looked at the project area of the Eaton Stormwater Spreading Grounds, which are shown on the top row of graphs there. I compared that to the NDMI of the surrounding area of those stormwater spreading grounds, which in this case was the larger city of Pasadena. It's interesting to note here, just looking at these two visualizations, that the NDMI for the project area and the city of Pasadena might not have the relationship that people would expect. The small sample size, at least of the project area for the stormwater spreading grounds, does validate that we have that full range of near 1 for NDMI, which is heavily vegetated and or saturated soils there potentially, all the way down to -1, which are very dry, open earth or bare soil areas. But what's interesting is to look at the graph on the right, which is the surrounding urban area, has a array of different higher NDMI values there. So taking that a step further here, I wanted to plot that out on a time series comparison from 2017 to 2022. And what's interesting is that the black scatter point dots there on the top is actually the mean NDMI there from each of those scene dates. And the green scatter point dots there are the mean NDMI from the stormwater spreading grounds. And this makes sense for a couple of reasons that I'll talk about here in a second, but I particularly wanted to take this data and then mesh that with the precipitation values of the daily mean there from iMerge. And what we do see is that there is kind of a more direct relationship or correspondence there between the stormwater spreading grounds mean NDMI in relationship to those precipitation data there. So where there were the very wet winters and heavy precipitation values there around winter 2017, 2018, and 2019, we do see large jumps there in that mean NDMI of the stormwater spreading grounds. We do see that correspondence a little bit with the larger city area as well, though that relationship isn't quite as severe. And lastly, I wanted to take look at the total array there of those TIFF files as well, to not just look at the mean values, which might normalize some of that data a little bit more, and look at the total range of array values there for both that project and city area. And in this case here, we have the kind of upper and lower quartiles of the ranges of those NDMI values, along with the mean values as well there. What we can see is there definitely is much greater variability in that range of NDMI for the stormwater spreading ground areas in comparison to the larger city area there of Pasadena. The mean area is also a lot tighter around 0 there than we would probably expect to see, and particularly compared to the city of Pasadena. There's a little bit more give around that mean and 50% quartile range. And that's a little bit due to, oops, sorry, let me go back here. And that's a little bit due to some of the irrigated area within the city. Quite honestly, there's a lot of irrigated area within these city areas and urban areas, whether it's residential lawns, landscaping, tree-lined streets, parks and green spaces. All of those ultimately have a large impact on the NDMI values that we're taking out of this analysis. And lastly, I wanted to kind of overlap the precipitation data on here, a little bit messier here, but you can see kind of the relationship there in between those upper and lower limits there of NDMI for both the project and city areas. What's interesting to note here is that on the graph on the left there for the Eaton Stormwater Spreading Grounds, we don't see as much of the lower limit of the NDMI values decreasing with that precipitation value or in dates nearing those precipitation falls. And primarily that is due to these stormwater spreading grounds actually being a combination of canyon area and wash, along with kind of a flat stormwater spreading ground area, particularly for the Eaton stormwater spreading grounds. And due to those terrain features, it's likely that a lot of the stormwater capture or stormwater flow going into that area kind of ended up basining or pooling into certain areas of that project area rather than the whole area. So overall, a couple of interesting findings coming out of this. Obviously, the surrounding urban area having a higher mean NDMI there than the stormwater spreading grounds was a little bit of a surprise, but it makes sense, again, considering the city has a lot more of that irrigated area and the direct measurement of NDMI as it relates to vegetation moisture index there. The stormwater spreading grounds did have a larger variability there, particularly in response to those precipitation events, which helps to validate the role that they are serving their purpose there to redirect and recapture that stormwater flow. But ultimately, NDMI in this case is probably not the best measurement here for accurate or adequately measuring that stormwater capture. Looking at something that is more directly related to soil moisture, like SMAP in that case, would be a much better way to measure this. However, again, the resolution ability of SMAP provides challenges when we're looking at these smaller project areas, particularly in urban environments. And in these cases, the stormwater spreading grounds are some of the larger green infrastructure type projects. If we wanted to look at things like bioswales and water retention ponds, those are much smaller and would need a much higher spatial resolution if we were looking to analyze those through remote sensing. And if I have the time, I would love to continue to build this analysis out here by looking at additional stormwater spreading grounds, analyzing the relationship there with stormwater gauge data, and even adding in the normalized difference in built up index as a way to measure the changing hardscape percentage of the entire Los Angeles area. It would be great to correlate all three of these factors there with how initiatives such as low impact urban development are changing the response of stormwater capture and discharge rates, in addition to the increased utilization of these different green infrastructure projects. So that's my presentation. Just wanted to thank everyone in the cohort here for their support here, and particularly Elsa for a lot of the guidance here with the code coming into this program. So thank you very much.